So let's start the next session. The next speaker is Ulf Kuhn from Hamburg, which is nice. So the play is over.
Okay. Thank you very much for the invitation. And I'd like to present a little step in a big program I have now since more than 10 years. So one is that I expect that many aspects of multiple zeta values are parallel to multiple q-zeta values. In particular, you also should have a coproduct, and this is how I hopefully derive one in near future. And this is based on joint work, in particular with Annika Burmester. We just finished an article which is on the archive just on the day today. So if you want to have more details, you can read it there. And also, we always had explicit computations in mind. And so lots of these formulas have been checked with computers, and we have made lots of examples. And so Niklas Konfúzius is writing a PhD thesis and is focusing more on this computational aspect. So what are multiple q-zeta values? So multiple q-zeta values are some formal power series with rational coefficient and some little q. And they are made in a similar way as multiple zeta values. You sum up over some integers which are nested some rational functions. And the main point is that if you let q, this little q, go to 1, and if you just modify it with a simple factor depending on these indices s, you will get back multiple zeta values. So multiple q zeta values are some particular deformation of multiple zeta values, and I'd just like to be brief on this. If you have seen them before, this will be enough. If not, I could spend lots of time on this and you won't understand the whole picture either. Okay, but the important point is they make an algebra, so you could multiply them, you end up in the same space. The multiplication depends on the choice of these polynomials you make, but it's easy to see that's an algebra. It is slightly different, difficult to define the weight and the depth, but you can do this. And then you could ask for conjectures about the dimensions of the weight, respectively weight and depth graded pieces of this algebra. And you get beautiful conjectures, similar like this conjecture of Zagier or Protos-Kreimer. So you see modular forms or dimension of the spaces of modular forms, and these are quite nice. And in particular, you could ask for subspaces. And so the subspaces I'd like to describe in a particular model with a so-called Schlesinger-Zudelin model. So there's the whole space where you allow these indices to become 0, which is different to multiple zeta values where you have indices not smaller than 1. But here you allow indices 0. And the last one has to be bigger or equal to 1, where for multiple zeta values you have, because of conversions, it has to be bigger or equal to 2. And then you could weaken this and say, okay, I want to have all these indices greater or equal to 1. And this is obviously a subspace of this space. And you could even go further and say, okay, I only consider those ones where the indices are just in this tiny set of 1, 2, and 3. And the conjecture we have that all these spaces are the same. Whether you go to the very huge space, you have lots of freedom, or if you go to a smaller one where you have, let's say, half of the freedom, or you really go to a very restricted one. And they are the same. And of course, for multiple zeta values, you have this theorem of Brown saying, okay, the space of multiple zeta values is spanned by those multiple zeta values which have entries just 2 and 3. And we want to prove this conjecture. And we want to prove it by following the ideas Brown used in his proof of Hofmann's conjecture. And so we need some more algebraic background. And for example, it is important to know that the algebra of multiple q-zeta values is a free polynomial algebra, or to be more precise, it's somehow the product of a space which is well known, the quasi-modular forms, and some commutative Hopf algebra. Actually, we want this commutative Hopf algebra just to be the graded dual of the universal enveloping algebra for some Lie algebra. And so we want a Lie algebra with a nice bracket, and also we then want to have a coaction on this thing. And then we want to understand the coaction on this little space to see whether this little space is preserved by the coaction, whether we could say something about a level filtration, and so on. And then if everything fits together, there might be a path that leads to proof of this conjecture. And I'd like to stress at this point that we looked very carefully into the proof of Brown's. And so in Brown is doing this for motivic multiple zeta values. And we spent a lot of time to separate which can be done purely algebraically and where you really need the theory of motives. So we were working in the so-called space of formal multiple zeta values. And it turns out that if you assume certain generation conjecture for the Lie algebra in the game, then it works fine. So somehow this is in the spirit of this workshop. So we have this double shuffle Lie algebra, and we assume double shuffle Lie algebra satisfies the same relations, because no relations as the motivic Lie algebra, and also there's the Grothendieck-Teichmüller Lie algebra and the Kashiwara-Wern, and somehow these properties of these Lie algebras then suffices to prove this theorem, and you find this also on the archive. Okay, and it turned out that in doing this rather new concept, namely the concept of a post-Lie algebra, was important for us. So the concept of post-Lie algebra is something rather new, maybe 30 years old. And meanwhile, I just checked it for the talk. There's about 100 references in the Zentralblatt in various fields of mathematics. It goes from rough paths to combinatorics to numerical integration. It goes to differential geometry and also to combinatorics and number theory. And that's what we are doing here. So what is a post-Lie algebra? A post-Lie algebra is a Lie algebra which has just another pairing. And the pairing should be compatible with the Lie bracket in the following sense. So it should let an element of the Lie algebra act as a Lie derivation. And also, if we let act a Lie bracket on a Lie element, then we should have these long relations, which is then expressed in terms of so-called associators. And the aim of this talk is that we present examples that are motivated by multiple zeta value or its Q analogs, that really this structure is giving us the information we need. And why is this so interesting? Because you can use this triangle to make a new Lie bracket, which we call the post-Lie bracket. It's also called the sub-adjacent Lie bracket. It's called the Grossman-Larsen Lie bracket. And as I told you, this is a rather new theory. Lots of different areas work on this, and so there's no common terminology so far. Okay, and now if we have a post-Lie algebra, then we could extend this post-Lie pairing to the universal enveloping algebra by having several axioms to be satisfied. So a general element X just trivial despite the constants. On constants, a constant X trivial X normal just as a one from the left. If you have a product on the left, then you have this associator stuff. And if something acts on a product, then you have to work with the coproduct you have on the universal enveloping algebra, and then we use so-called Sweetler's notation. And so this extends unique to a bilinear pairing on this universal enveloping algebra, and then you could rephrase this more complicated axiom that a bracket acts just as you'd like to have it. So this is then just the ordinary concatenation in the universal enveloping algebra, and then you know how to resolve this by these equations, and then you get these four terms. Okay, and then the theorem we use the most is that you can now use the triangle to define a new product on this universal enveloping algebra, the so-called Grossman-Larsen product. So again, using Sweetler's notation, so you have to take the coproduct of A, and then you have all these possible summands and to get this. And then it turns out that you get another Hopf algebra, and that is that you could say, or people say that this universal enveloping algebra with the usual coproduct and concatenation product together with this extended triangle is a so-called post-Hopf algebra. So it's something, it's a Hopf algebra, it has another map which has some compatibilities, and then you get again the so-called sub-adjacent Hopf algebra. So in the way as we get from the Lie algebra with a triangle, another Lie algebra, we could use the triangle on the Hopf algebra, we get another Hopf algebra. And the point is that if you have this new Lie algebra with a new bracket, then of course it has some universal enveloping algebra just by concatenation and the shuffle coproduct, but you cannot do any calculations with this. But here you have an explicit isomorphism to say this Lie algebra is just embedded in this space here, and now the multiplication is with this Grossman-Larsen product, but you still have the shuffle coproduct. And so the bracket is then just the bracket of this associative algebra. It's something like, you know, for matrices AB minus BA. And so it's not concatenation. And this is by Ebrahimi Fahd, Montekas, Landerfold. And this is the nice thing. And now, how does it look like? So if you have elements in the Lie algebra, then this Grossman-Larsen product is not too bad. So it's just concatenation and the triangle. And so this complicated post-Lie bracket, or you know, which will be in some slides later, will be called the Ihara bracket, can be now expressed just in terms of this Grossman-Larsen product. And also you have for group-like elements, okay, now you have to do completions, but just for completeness, to make it in brackets, so then you have this formula here, and this is a formula you know from the Magnus-Tordu action, also in the context of Racine and so on. And the point is, you could calculate this Grossman-Larson product by using this definition, how this triangle is extended, and it will be a big mess and lots of terms and so on. And so if you want to do explicit calculations, you somehow seek for better solutions how to calculate this. Oh. So A1, A2? So this is this so-called iterated coproduct. Let's see. So we have delta of A equals A1 tensor A2, which is somehow the sum of lots of these AI tensor some AJ, and this is Sweetless notation is just that you, oops, sorry. And now this is a co-associative. Now you could apply delta again, and then you get these terms and terms. So if you delta of delta, and then it just doesn't matter whether you apply delta to the second or to the first term, and then you could do it iteratively. Okay, and so somehow the picture is that if we have a graded post-Lie algebra, so this means that the vector space underlying the Lie algebra has some grading, and we want these spaces each to be finite dimensional, and then we want that the ordinary bracket just adds the degrees, and also this triangle adds the degrees. So then we have a grading, and then we get an induced gradings on these Hopf algebras, and then we have now the following picture. So we start with our Lie algebra, then we go to this graded Hopf algebra, then we could make the graded dual. So we just make the dual on each graded step. And then we get that the shuffle goes to, the shuffle coproduct goes to the shuffle product, the concatenation goes to the deconcatenations, and then we could identify modulo products, the indecomposables which is a co-algebra with this Lie algebra. And also we could play the same game now with the Grossman-Larson product. And then we get a coproduct corresponding to the Grossman-Larson product. And okay, we get also this co-algebra. But this is what we want to do. And we want to, for example, see Goncharov coproduct somehow here as being dual to the Ihara bracket. Okay, and now we want to apply the theory of post-Lie algebras to free Lie algebras. So for this, we have to fix a countable set. And so we just start V0, V1, V2, and so on. And we call the elements letters. Then we denote by V star the set of words in letters. And so we could also say V is an alphabet. And then you just make words. And then you also have the empty word. And for notational reasons, we want the empty word also be an element of the words. And then we have the free non-commutative algebra equipped with concatenation. So it's just if you have words, you make them longer. So German is a language where you have lots of these words, like Donau, Dampfschifffahrtskapitänspatent. So it something means that the guy who's on the ship on the river Danube is a is the chief of the boat, and he has a paper signing that he's the chief of the boat. And so you really have these long words, and the same you do here. And in the side, you have the free Lie algebra, which is the Lie algebra just generated by Lie bracketing the letters of your alphabet. And so this is a subspace in this set here. And then it turns out that the universal enveloping algebra of this free Lie algebra is nothing else than this QV with concatenation and the shuffle coproduct. And we just fix a duality pairing, and then it is more convenient to identify the dual of V just with V. And so the dual of the, let's say, the shuffle coproduct is then just the usual shuffle product, which is just given by this formula that you shuffle the empty word and you get the word back again from the left and to the right. And then if you have a word and you have some VI and VJ in the front, then you just make this sum here, and then you extend this Q linear to get the shuffle product. So it's something you find, for example, in the book of Reutenauer and so on. This is standard. Okay, now how to calculate the coproduct? So the naive way to calculate the coproduct is just to calculate tables with a large number of Grossmann-Larsen products, and then just use the duality, saying, okay, the coefficient of F tensor G in the coproduct of this word here is just the coefficient of this word in the Grossmann-Larsen product of this multiplication. So you could do this. You could make tables like that, 2000 times 2000, and then you could just transpose the rows, and then you calculate the coproduct. So you could do this. Maybe it's not efficient, but it works. And actually, the Grossmann-Larsen product was working with this triangle, and you had this decomposition with a coproduct. So, and then you have to concatenate terms with this triangle. And actually, if you work in a free Lie algebra, you only need to know these cotriangles for tensors where you have a word to the left and a letter to the right. So instead of calculating all products, you have to calculate only the triangles with where you act with a general element on a letter, and you have to understand the words which occur in this product here. And then completely abstract, if you have an alphabet and you have a graded post-Lie algebra, then you could really express this coproduct here by the sum over all decomposition of A. And then you have something which is, you take A1 tensor 1. And now you have a kind of new multiplication. And the new multiplication is that on the left, you just multiply the factors with shuffle. And on the right, you just make concatenation. And so the point is now, you have the second factor, which is again something of a tensor. And so you calculate this. And then this gives you the coproduct. Somehow you just reversed in a general way the formula for the Grossmann-Larsen product, and then you have this formula here. And of course, later we will make this explicit. How does this cotriangle look like? Can you make a nice formula? But this is just the formula you have. Okay, and now we started to have the theorem saying, okay, let V be a Poisson algebra, but how you prove something is a Poisson algebra. So that's the next question. So you have something, but you want to have it. And it turns out, at least for our examples, is that you really play the game of algebra. So you go one step further. So if you look in the book of Serre, for example, how does he introduce the free Lie algebra? He says, okay, consider the magma. So you just squeeze letters together in any way, and you make any bracketing, and then you make a quotient by dividing out a certain ideal. And this is what we do here. So we extend somehow the notion of a Poisson algebra to a Poisson magma. And so we have a magma, so it's just a set with some operation. It has to satisfy no rules at all, a priori. And then you could squeeze lots of these operations just by bracketing. And now you can consider derivation. It's a map that's respecting this pairing. And now assume we have a free magma and we have another map. And it's given like this. And then we could extend this as a derivation, because here we have just a simple element. So we could extend this by the rule here as a derivation. Okay. And so we could view this new map here as a bilinear pairing on this MV. And now we could make the free non-commutative but associative algebra on this huge set M of V. And we can extend again the triangle. Okay, so we have lots of the same kind of rules which has to be satisfied, but we have just a very big space and we have this triangle and this is fine. And now we just want to go back. And then we remind there's a map from the magma to the Lie, just saying, okay, if there's a star, just make a bracket and say this is a Lie bracket. And you just have the kernel that these elements here are in the kernel. So this means that this is alternating. So it's antisymmetric, the Lie bracket. And it satisfies the Jacobi identity. That is the only relation a Lie algebra has to satisfy. And so we are done. Okay, and now if we keep everything together, so we have this alphabet V, then we have the free magma, and we have this triangle pairing. And then we say we get a post-Lie algebra if this maps descends to a bilinear pairing on the Lie, and if this relation here holds. So this is just one relation, and then you want to prove this. Okay. So it's fine. I'm almost in the half of my talk, which is now we can apply this. I have 3 examples prepared. And the first example is something which is just showing that this theory is meaningful. And then we come to newer and newer examples, because this is something you should be familiar with. And so we just want to show that the stuff you know by heart is just an example here. So we do it slightly more general, because we now allowing a bigger alphabet. But if you're really close-minded, to just think of V to be V0, X0, X1, and V0, and the big V0 just to be X0, but you could take any things like that. And so you just have this magma paired with V. You say, okay, what you have to do? Okay, I just have to multiply in the magma with a V. And this is if V is not in this exceptional map V0, and if it's in the exceptional map V0, we just send it to 0. And then we extend it as a derivation to the qm of v. And now it descends to Li of v, because what we do have to check, so on the one hand side, because we extend it as a derivation, then it's clear that the derivation of this ideal for the Li is again in the ideal of the Li. And to the other one, it's just clear that it also maps something in the ideal, because you just multiply with v. So it is then again in this non-associative ideal. So it is clear that it descends, but there's another thing. We have to prove another identity. And now somehow there comes the trick. So we have a formula which translates this complicated product in this free associative non-commutative algebra, where you have these concatenations of elements in the magma, to a multiplication just in the magma, and it's doing by this iterated multiplication in the magma. And this is an easy step on induction and just applying the rules how you multiply these complicated elements, and then you have a kind of telescoping sum, and in the end, just this one survives. And this is somehow the key that makes everything accessible, so that you really have this a priori complicated formula where you have, it's like an n faculty of terms, but on this n faculty of terms, only one is left. Okay. But now it is rather easy to see that this triple is a post-Lie algebra. So we have to check this thing here, but this is just by definition here. And so we have this expression here, but this is using this lemma just given by these terms here. And now we have to apply the Lie map to this expression here. So we just have to replace the stars with a bracket. And then we get Jacobi identity. I'm happy, it's 0, it's fine. So we see on rather 2 pages that the Ihara bracket gives us a post-Lie algebra. And okay, I said already this is the Ihara bracket. And but now we want to go further. So we had now this extension of this triangle map to the universal enveloping algebra. And how does the multiplication of with respect to this triangle looks like on this enveloping algebra? And then it is essentially that you multiply with the antipode of the first factor of the coproduct with the second factor of the coproduct, and then you add over all these terms. And now you have to take care that where this V0 belongs. So if the V0, of course, belongs to, if the V belongs to V0, then we have this different multiplication. So we just put this into this character stuff here. And so if the A is the 1 and the V is the V0, then it is fine. If not, you have this formula here. And again, it is just using this formula here. And now you have that you can resolve the brackets in a Lie algebra just with the coproduct. Okay, so you are done. Okay, so you have this nice formula. And having this formula, now we have this complicated formula for the Grossmann-Larsen product, but now we could just replace all these tiny bits in here, in here, in here, and we have somehow to take a little bit care of the words of the letters in V0, but we get some completely explicit formula. And so this is fine. And now we could also calculate this code trace. And now this code trace is given by decomposing these words into the letters. This will be a factor on the right. And to the left, you have all these shuffle products where you have to somehow take care whether this AJ is in V0 or not. And this is what this I should take care of it. So the I will be just the identity if this AJ is not in V0, and it will just measure if the remaining part is just the empty word, then you will get 1, otherwise it will be 0. Okay, so you really have this here, and it's completely explicit. And now you get this general formula. So you have these words in V. You could write down the coproduct, and then you get a formula. You have this multiplication to the right. It's just concatenations, and you have factors on the left. And if you look carefully, you see it's very similar to that formula of Goncharov, where you have this half circle and you have these lines. And the point is, somehow you have to get rid of this I, because this I is somehow separating the parts which belong together in Goncharov's coproduct. So it's somehow here. It is those that would belong to Goncharov's coproduct, and then this thing here, and this one will be alone. And now the point is you have to play the game, what's going on with the I, when it's 0, when it's not 0. When it's non-zero, then it may happen that this shuffle is vanishing because of the antipode relation, because you are now summing over all i's. And then if you just shuffle a word and you apply the antipode to one of the factors, then it will be 0, because this is the antipode relation in this shuffle-Hopf algebra. And then you just get back Goncharov coproduct. So the point I want to make here is that we have a completely algebraic way to obtain exactly Goncharov's formula for this alphabet here. We completely avoided any use of iterated integrals. We did not speak about any paths. We did not went through completion. This was what we did in our formal multiple zeta paper, where we had to go through completion. We completely avoided, no, we avoided completion totally, not completely, so it's a double. And so this is why I'm happy to present it to you. So it's a really clear statement. This Goncharov bracket has dual coproduct given by Goncharov coproduct, and completely neat. Okay, now multiple q-zeta values somehow use the full force of a Carlism. So it's not only using moles, it uses b-moles, and everything is slightly more involved. But we are able to translate this into this language of free Lie algebras in an infinite alphabet. And so the first thing is that the notation becomes more and more complicated. And so we just recall that this free magma can be described as planar rooted binary trees with leaves labeled by elements of V. So somehow the recipe is whenever you have a knot, then you just put a star. And so you get that this tree is corresponding to such an element in the magma. But here you have a very nice order of these elements, and now you just view the tree as being a function on d copies of V. So you just say, okay, you plug in this on the first leaf, this on the second, that on the third. So it's really that you view a tree as a function on its leaves. Or you could say a magma is somehow the rule how to bracketing, and you could plug in just the elements you want to plug in. And so we just write, therefore, T of VK1 to VKD, or even more general, we just write T, and then we say K1 up to KD, because whether we say VK1 or VK1 or K1, we don't lose information. So we really now consider somehow these elements in the magma, because we have chosen a numbering of our letters just to be a function on indices. Okay, so, and now having indices, we can define multiplicities. So we define this ARI multiplicity by having a sign, which is just the sum over all these entries in this multi-index. And then we have binomial coefficients. And in order to make formula more smoothly, we make this convention if the entry is -1 and the upper one is 0, or vice versa, it will be 0, and -1 over -1 is 1 in this. Okay, so this is just some binomial coefficients and so on. And then we could define finally a triangle. And so the triangle will be that I have an element in my magma, which is now indexed by some K, and it acts on some VA. And now what is going to happen? So the index of the VA, okay, it's going to 0 if VA is 0. So this is fine. So the exceptional set is just only one element. But now if it's not V0, we are increasing the index of the A, but we are decreasing the index of the T. And we go over all these indices multiplied with this multiplicity. And this multiplicity is taking care that there's no strange things happening. So it will be finite. And so it also takes care that, yeah, that this is well defined and so on. Okay. And now, again, it's not too difficult to show that this pairing on the magma descends to a pairing on the Lie algebra. And we have, again, a nested formula, which now becomes more messy. But you still have this formula. And latest here, you see that it was quite useful to have this notation, because otherwise you don't know how to keep track which element has which index and so on. And so it really helps you to get this. And now to prove this formula, you really have to keep track of these multiplicities, and then you multiply the terms you want to multiply. And then at the end, you have to show some identity of the multiplicity. And so this is some identity of for binomial coefficients, and this you can prove, let's say, by generating series or some standard number theoretic methods. So it's really somehow you prove this lemma by proving some identities for binomial coefficients. And to make it then work, you again want to show that you get a post-Lie algebra, and then you plug this in, and then you're happy that you get a family of Jacobi relations and everything works fine. And if you really love to see the details, I just said it's on the preprint, which is on the archive. Okay, so I will be quick on this. Okay, and it turns out that this Poisson bracket is the Ekal-Ari bracket. If you translate it correctly into the space of polynomial B-moles. And this is something you find in the preprint. And so now we have again this extended pairing on this big algebra QV. And so we want to see how does the Grossman-Larson product look like. And again, we need to understand how these triangles look like. And then we could get a formula for this Grossman-Larson product. And again, the message, this can be put into a computer, and it takes a millisecond to calculate this, even so it's enormously long formula. And so it's really a good way to do these calculations. And now we can lean back and to say, what did we achieve? So we have some Hopf algebra, so we could ask for sub-Hopf algebras. So we see that, for example, if we just take these strictly positive letters, then we get a sub-Hopf algebra in here. We could also consider just V0, V1. Then we get some sub-algebras. And actually, this is just the Ihara Hopf algebra we had seen before. And so we really have some nice functorialities. Also, we have some way to describe the orthogonal complement, or rather to say it's the commuting complement, which is then on the Lie level, the orthogonal thing. And so we could play on this. So we have some things. And also we have, which is notationally a mess, but we have a way to determine these cotriangles. So it's just a long formula. And then we can use the cotriangle to give you a formula for the coproduct in this for this Ekal bracket, which is something new, which never occurred in Ekal's work. Is it correct? And so we just went further, and I have no idea how to express such a formula in terms of polynomials, but we have this here. And then we could look on the space we are interested. We are interested in this space of words in V1, V2, V3, and could ask what's going to happen with this coproduct. And then, oh, we are happy the coproduct is preserved on the right factor, which is something what's important in Brown's proof, namely that on the right factor, the 2-3 words are preserved. Then there was a so-called two-level, and this level concept is also working for this coproduct, but we have not proven it yet. But now we are in the lucky situation, we have this in our computer. So I could tell you there's 2,000, 3,000 cases, we checked this. And if you see the formulas, it's not random, but it's only a lack of time, it's a lack of brain or something that we have not proven it. But somehow we have really now a gadget to say substantially, we believe this is true because we checked this, and it's not like, I think maybe. So I'm very happy on this. Okay, so we have this. But unfortunately, the world is more complicated. So in the language of multiple q-zeta values, we just described the the Lie algebra in the depth graded version. But we don't want the depth graded, we want the depth filtered one. And so the multiplication becomes longer, and I still have 10 minutes. And so I be brief and just give some impression what's going on. So you have more multiplicities, and these multiplicities have a new feature which is, I think, remarkable. So if we fix a threshold A, so just an A in N, then we could ask in a partition, what is the first index such that the sum of the first entries is bigger or equal than A? So it's really somehow it distinguished in this composition, okay, at this step you're over A and not before. And now with this, you could define a multiplicity depending on some index and this threshold. So you have now two numbers. So you have this threshold A and you have this indicator function depending on the threshold. So this is two variables, and you use these two variables to be somehow the coefficients of some function, and the function will be this one. So you have the M and you have the K, and the K is somehow determined by the N. So it is a linear combinations of, oops, I missed to say, this is of course the Bernoulli number Bk. And so you have this thing here, and now the statement is that this triangle is now given by this pairing here, where you have this element in the magma. Again, if VA is V0, you're fine. But now you multiply with TL as before. But what you're doing now is just to decompose the first guy and to make, again, this longer. And then, of course, you have a decomposition of the index you had in the ARI case. And but the original A plays the role of the threshold, and this is reflected in this multiplicity here. So it's really a kind of combinatorial, more difficult thing, but you see now you make this A longer. So in the Ihara, you keep this fixed. In ARI, you let the index bulk here and to increase the index here. And now you decompose this and you get higher depths. And again, this descends to a Lie algebra. Here, it is already a pain to prove this only for two factors. And we have conjectural formula how it looks like for more factors. But somehow you see there's a mass of these multiplicities. Then you have this index decreasing of the T1, T2, and then you have alphas and betas. And these are compositions depending on the parts of the composition of the alpha and so on. But it has some compatible meaning. And then, again, to prove this formula, you end up by a comparison of coefficients. And then you see if this multiplicity satisfies this, you are done. And this is, again, proven by binomial coefficients. And now the theorem I want to present is that if Bernoulli numbers satisfy what we call the threshold shuffle identities, then the Uri triangle determines a post-Lie algebra. And the way to prove is, again, to multiply and then compare two sides, and then you get identity for the coefficients, and then you have to extract what are the identities for the coefficient, and then you have to check the multiplicity to satisfy this. And then we get this. And why we are kind of happy? Because we have now 3 versions for this Uri bracket. So again, one translated into the space of symmetrical polynomial B-moles. Yeah. So I'm and I mean B-moles. Okay. So, but in this first alternil. Okay. So, and the point is that these maps here produce poles, and this one produces poles, and you don't know whether these poles disappear or not. And the combinatoric is in such a way that we were not able to determine the relations which has to satisfy in a, let's say, in a packed way, that we could say, okay, if the following number theoretic identity holds, then there will be no poles. Something like if 1 + 1 = 2, we have no poles. But so the theorem 20 is somehow, we were able to give a complete description saying, if this identity holds, then this will be fine. And so this is somehow the advantage we had before. And of course, you could check these identities with a computer, and everything will be fine. Okay. And so this is somehow we were happy about. And we then can use this in a way that we derive to some Racine type description of these multiple q-zetas and so on, but then it will be needed another paper saying that this potential Lie bracket is well behaved with respect to some involution, which is again not clear how to prove this, but then we come more and more towards the step of proving this 1, 2, 3 conjecture. And I see I have 3 minutes left and 3 slides. So the point is that we have time to say what are these threshold identities. And so we have these multiplicities, and these multiplicities depend on an index in the second argument, and we make the second argument somehow a function on the indices. So we could now extend it to formal linear combination of indices and so on. And also we could decompose indices and so on. And then we really get some messy formula. So somehow we have some indices, and we decompose the indices. And out of this, we just make these threshold indicator functions, and we have lots of shuffles and concatenation of indices. So it's a completely explicit formula. You could take it, put it into your favorite computer algebra system, and then you check this. And then, of course, so these Uri multiplicities are obtained by considering a particular Taylor expansion of a function like this. And then if t = 1, you just get the Uri multiplicities. And it seems to be the case that somehow this function governs this shuffle threshold identities. Okay, so I'm happy that you stayed interested.